Year 12. Hopefully, this is my final take. I don't have to do it again. And hopefully the final video. I can delete that awful YouTube channel and evidence of this hair can be gone forever. Now, we are looking at simple harmonic motion again. It says SHM3. I think it's only the second one. I decided to scrap the second one that I did make. I was going to put out yesterday. I thought it was more confusing and it was something you didn't really need to know. It was just again about the link between circular motion and SHM. But today we're going to look at how the graphs and the SHM equations work. So we're going to look at displacement, velocity, acceleration graphs with respect to time. We're going to look at them as equations as well. And then we're going to use other equations that also deal with SHM. Now, when doing this, always have the picture of a pendulum in your mind. Even better, make one for yourself. Okay, pause the video and make one, just so you can see that movement of to and fro. Okay, and you can see what I'm talking about from that little diagram there. Now, the last PowerPoint you saw was basically defining what SHM was. Okay, so we get it when we get an oscillation about a midpoint. But its true definition is when the acceleration of the object is directly proportional to its displacement, and it's always directed towards the equilibrium point. So A is proportional to minus x, okay, and they've got the graph in the bottom right-hand corner there, okay, going through the origin. And then we can turn that proportionality into a formula with the constant. Now, the constant, remember, is omega squared. Now, that should get the reason why that is the case in today's video. Now, another important thing is omega. Okay, in circular motion, omega was 2 pi f. Okay, and omega was angular velocity. Now, we still use omega in this, okay, but it now means angular frequency. Okay, but it's still 2 pi f. Everything else is the same. We just call it angular frequency rather than angular velocity. And the reason for that is its speed is going to be constantly changing during a pendulum. Okay, it's going to accelerate and decelerate constantly. So that's why we've changed the name and call it angular frequency. And all the formulas in your formula booklet use omega. Pretty much every question that I've come across uses the frequency f. Okay, so wherever there's an omega, you can just replace omega with 2 pi f. So let's get on to looking at our first graph, the displacement time graph. So if you displace your pendulum to the left, positive, in this case, okay, look at where the graph starts. Okay, and if you release it, okay, the displacement is therefore going to decrease as it gets towards the equilibrium position, and then it's going to increase as it moves away from it to the maximum displacement on the other side. And remember, a maximum displacement is what we call the amplitude. Okay, so we're moving all the time from the positive amplitude through the equilibrium and then to the negative amplitude. And it'll repeat that. And you can see after one time period where t is on the graph, we've gone through that one cycle. Okay, so we start on the left, we've gone through equilibrium to the right, back to equilibrium, back to the left. We've gone through that one full cycle then. Now, if we increase omega, angular frequency, well, the effect that would have is it would just make everything closer together. Your amplitude would remain the same, okay, but you're getting through your cycle faster. So your time period is going to be a smaller amount of time. So all your peaks are going to be closer together. Okay, technically, I've just took that graph and I've just squished it up a little bit. I should have kept the axes the same and just moved the line. I don't know how to do that. So there's our first graph. Now, if we think about the equation, the first thing is you can see that is following a cosine curve, that first part of it. So just look up to the first time period. That is a cosine curve. Therefore, if we want to know the displacement at any point or after any amount of time, okay, using the cosine is going to be really important. Okay, now the other things that are going to affect where your displacement is how long has passed. Okay, so greater amount of time has passed, you're going to follow greater or further distance along your curve. Also, if you've got a greater angular frequency, you're going to get through this a lot faster through a full cycle. So those two things are going to affect where you are in the curve, and obviously your amplitude will as well. Okay, your total displacement, if your amplitude's higher to start with, okay, you can obviously have different displacements than if your amplitude is lower. So the equation that relates to this is this: x, your displacement, is equal to a, your amplitude, cosine omega t. Now remember, omega is 2 pi f, so we can stick in there that x is a cos 2 pi ft. So that's our equations for displacement. Okay, so all of these, remember, this whole thing, all cosines have to lie between plus and minus 1. So your amplitude then scales it up, okay, or down, depending on what your amplitude is. Now, if we also look at the curve, we can see at the very top here, there is zero gradient. Then the gradient increases and reaches maximum gradient as it passes the equilibrium position, and then the gradient will decrease as we get towards the opposite end of your pendulum, and then it'll increase again. So if you think about your displacement time graphs, what is represented by the gradient on a displacement time graph? It is velocity. So when we come over and we look at the velocity time graph, it's going to look like this. So in the displacement time graph, we had zero gradient to begin with, and then the gradient increased. But if we go back, you can see that the gradient is negative. So we have that negative gradient. Here we reach a maximum velocity as it passes the midpoint. It's then going to slow down until we get to the end again, increase as we pass the midpoint, and it's going to decrease again back to zero. Now, if you look at that graph, what does it look like? Well, it's an inverted sine graph, sine curve. Now, if you also think about your maths, the displacement time graph, if you get to get your gradient, you would differentiate that graph. So if you differentiate your displacement, you get that. You get minus omega a sine omega t. So the negative, you can see it's a minus of the normal sine curve, and this minus omega a, or omega a, again scales this. So this point here would be omega a, minus omega a, here would be plus omega a. Yep, so there we go, omega a. Now the acceleration time graph, again, just thinking about the definition of SHM, you have your greatest acceleration and your greatest displacement, but it's in the opposite direction. So when you look at this, the displacement one started here, this one starts here, it's the opposite. Okay, but it's also at its greatest value. And what that tells you is at the ends where your pendulum changes direction is where you get maximum acceleration. Okay, now its acceleration reduces as it tends towards the equilibrium position, and then it increases again as it gets towards the far end. And again, it follows that cycle. It is exactly the opposite of the cos graph. But again, if you took your velocity equation and you differentiate, because remember, this is the gradient of your velocity time graph, you get that. Acceleration is equal to minus omega squared a cos omega t. And since x equaled a cos omega t, the acceleration therefore is minus omega squared x. Okay, and that shows it is an SHM situation. Acceleration is proportional to displacement. This value here will be equal to minus omega squared x. And so we can get information from graphs. We can use it often to work out what omegas would be. Okay, what x's, what a's would also be. We can get quite a lot of information. There we go, added that on. So if we put them all together, displacement time graph, velocity time graph, acceleration time graph. So if you look, there's our displacement one. If you take the displacement and you shove it to the left by a quarter of a cycle, you get your velocity. You take your velocity and shove it to the left a quarter of a cycle, you get your acceleration. And we can see the velocity time graph is the gradient of the displacement one. The acceleration time graph is the gradient of the velocity one. Okay, and then there's our equations that govern our graphs. Okay. So I'm going to go through one or two examples. Okay, and then I'll send you a PowerPoint. Well, I'll send you this as a PowerPoint as well. And there will be extra questions on the end of that one to do. I'll give you more information in the email. So the pendulum of a grandfather clock has a time period of 2 seconds, calculates frequency and its acceleration 50 millimeters from the midpoint. So frequency is 1 divided by the time period, so it's 1 divided by 2, so it's 0.50 hertz. So we've got its frequency. Its acceleration is equal to minus omega squared x. We've got to use that one and not the one with minus cosine, because we haven't got a time it's asking for. It's asking at a certain distance we've got. So we stick in the formula. Because we've got a frequency, we can put in the 2 pi f for our omega. We stick our numbers in. Remember, we've got to use SI units, so your 50 millimeters has to be in meters, so it's 50 times 10 to the minus 3. And we get an acceleration of 0.49 meters per second squared. Second example. Plucked guitar string vibrates at 260 hertz with an amplitude of 2 millimeters, 2 times 10 to the minus 3 meters. What will the displacement be after 1 millisecond? Now, one of the things I haven't mentioned yet, and it's quite important, is your calculator, when using your sine and coses, has to be in radians mode and not in degrees mode. Okay, so just be careful, and when not doing SHM questions, make sure you turn it back, or you'll always be getting the wrong answers afterwards. Many a mess up on an A-level paper has been because we've had the calculator in the wrong mode. So x equals a cos 2 pi ft, so we're after displacement. So its amplitude is 2 millimeters, so 2 times 10 to the minus 3 times cos of 2 pi times 260 hertz times a time of 1 millisecond. You're bugging it into your calculator, and you get a displacement of minus 1.3 times 10 to the minus 4. So the minus means obviously it's on the other side of the equilibrium. Now, I hope this has helped, and have a go at the questions and see if we are okay with them. Hopefully see you soon.